The goal of this project is to develop an algorithm for image generation using few-shot data for GANs. Ideally, I would like to explore novel architectures and structures that have not been seen before, and also structures that are applicable to classification and regression tasks. This slide talks about some of the previous works that have been done before in this area. As you can see, most of them use an existing algorithm like MAML and combine it with task-specific approaches to do well on their test task. This is the upper-level architecture of my algorithm. Notably, we have an adversarial oracle that functions as a critic, which prevents the upper network theta shared from encoding any task-specific information. So the objective is to encode a shared structure in theta and task-specific information in phi. Also, we would like to ensure that we don't encode task-specific information in theta, and ideally we do not want to encode any information that's common across tasks in phi. But how do we do this? How do we ensure that this objective is met? So I'm actually using an adversarial objective to ensure that the shared network does not output any task-specific information. I've also provided a method to supply labels to the critic in this slide. There is a downside in using an adversarial objective. The theta network can always learn to output a constant, say ones or zeros, and fool the critic. The loss objective is not going to help us because the phi network will absorb the structure information and do well. We need to also penalize the phi network. This will force the theta network to learn meaningful representation. So formally, we would like to minimize the mutual information between theta and phi. If you go through the math, this is equivalent to maximizing the KL divergence between z given phi and z given phi and theta. This is, however, not an easy problem to solve because the KL divergence is convex and we have multiple solutions that do this. Instead, we can use the Jensen-Shannon divergence and penalize the discriminator loss when these two quantities get too close to each other. And it's also very easy to do so because we already have a discriminator that is anyway doing this. So this is the overall loss objective. So the first term here is to generate realistic looking fake images. The second and third term penalize the JS divergence between the distributions that we saw previously. And we also have an additional term that constrains the theta network to only output shared structure. So most of the experiments were conducted on MNIST, taken about 25 images per task during train time as well as test time. So let me quickly go through the images and talk about the observations. So the images on the top left represent the images of the network, the actual fake images generated by the generator. On the top right, we have images generated when we do not use shared information. On the bottom center, we have images when we use only the shared structure. The top green image, that's representing the output of the task-specific network, and the yellow image is the output of the shared network. And on the bottom right, we have the test image with an FID of 46. Finally, will this algorithm converge? That depends. It depends on the the function classes that we use for the estimators, especially the encoder and the decoder. Ideally, you don't want to use a neural network there, although I have used a neural network here. You want to use just a transformation network that does not encode any additional information. Also, the loss functions play a role here. We do not converge when we use vanilla GAN loss or binary cross entropy loss, but in practice I'm observing that the algorithm works quite well.